Professor Gražulius is a senior researcher and professor at the Vilnius University Institute of Biotechnology. He received his PhD in 2000 in crystallography at the Munich Technical University in Germany, under supervision of Professor Robert Huber. His work involved crystallographic investigations of proteins and protein DNA complexes. After completing his PhD, Professor Gražulius returned to Lithuania, where he worked as a researcher at the Institute of Biotechnology. Later, the institute became a part of the Vilnius University. His work involved structure determination of DNA protein complexes using X-ray crystallography and crystallographic data management in the Department of DNA protein interactions. Since 2005, Professor Gražulius started collaboration with the maintainers of the crystallography open database. From 2007, he leads the effort of server development and data curation of the crystallography open database and related sister databases, including T-Code, the theoretical crystal structure database, for archiving and disseminating data of crystal structure obtained from DFT computations and other theoretical methods. Professor Gražulius has published 53 papers so far. He will talk today on open databases, what do we have, where we are going. Professor Gražulius, the screen is yours.
Thank you very much for this very kind introduction. I am indeed honored to be here and to have opportunity to deliver this lecture. And I want to share with you some of my experiences and efforts which I gained during management of data and creation of data in the crystallography open database. And hopefully we can discuss how to improve quality of open data resources that you can use for many purposes, including quantum crystallography, and also maybe how quantum crystallography could contribute to improving data in these databases. As you know, data is extremely important in all fields of science and in crystallography especially. And crystallographers are really at the forefront of data management and sharing data in digital form. Actually, the first papers which I encountered on using digital computers and crystallography go back to 1943 by Linus Pauling, and actually these are probably the first years when computers became available for scientists. So crystallographers really jumped onto this opportunity. And if we look now at the numbers of structures that we have for published protein structures, for published small molecule structures, and I know that some people don't like word small, but in this context, they are small relative to proteins. Otherwise, we could say it's chemical crystallography structures. And also, if we look into numbers of known chemical entities, we would get numbers something like this. For the open databases, the Protein Data Bank, the worldwide resource for protein and nucleic acid and other biological macromolecule structures, has recently passed the mark of 200,000 entries. The crystallography open database, which we are maintaining in the Vilnius University, is approaching 500,000 structures. And there are other open resources that are smaller, but they contain very peculiar, hand-curated, well-picked up structures, such as Bilbao magnetic data or incommensurate data structures. So you see that in principle, all the field of open databases is getting close to 750,000 of structures and is growing. Oops. Okay, next slide. Of course, there are a number of commercial databases which are larger than the open resources so far. I must mention the Cambridge Crystallographic Data Center that established and curates and distributes CSD, the CSD database, Cambridge Structural Database, the Inorganic Crystal Structure Database, and the Powder Diffraction File also contain data on inorganic materials and powder data, while the CSD used to contain mostly organic materials. And then there are more specialized files like polling file that is a hand-curated resource of material structures and material properties. And to my knowledge, these resources together have close to 1.5 million structures. And what my point here is that we probably, at the moment, in the whole scientific community, have between several millions of reliable scientific crystallographic records. And the point is that for such numbers, we need to use computers and organize databases, but also when we have such large amount of data, the quality issues become important. I will now concentrate on the database which we develop and which I know the best, the Crystallography Open Database. It is available online for the last, for more than 16 years by now, and we are accumulating small molecule, that means organic chemical crystallography structures, organic, metal organic, and and inorganic mineral structures as well. Each structure can be viewed individually on our web pages, and each structure has a dedicated web page for it that allows you to investigate it visually and also to have access to the most important crystallographic parameters of that structure. But also, being the open crystallographic database, the COD allows you to download the whole set of our crystal structures without the need of registration and free of charge. And you can use this for high throughput computations, such as machine learning, quantum mechanics computations on your own computers. And also you can use it for teaching purposes, distribute to your students, and use in a similar setting, in similar settings. Okay. When we now start thinking what we expect from a database and how we should set the quality criteria for the data that we have, actually I start thinking that it's not only the internal, so we can set up two kinds of criteria. The internal criteria that relate to the to how good our data explain the observations in the physical world and how accurate the data are. But also what is important is how data in such amounts are accessible, how they can be distributed, found, and these properties are also very important if you want to use that data efficiently. So I would say that data should be fair, and this is an acronym which we will look into deeper in the next slide. Data must be, I want to emphasize this, must be machine readable. And the reason why we accumulate data at all is, of course, to support our scientific conclusions. So data should be scientifically sound and valid. And this incorporates all quality criteria and numeric quality criteria like correspondence to the observations, R factors, goodness of fit, internal consistency, and similar parameters. And recently, it's becoming more and more important that data should be open. Actually, it's also discussed even on as a political mandate from the European Union that data should be as open as possible and as closed as necessary when the full openness is not reasonable. Therefore, open databases, I believe, have very high potential in the future. So let's now look into how well the crystallography database scores on the FAIR principles. FAIR in this context means that the data must be findable, accessible, interoperable, and reusable. And the very principles have been summarized and published quite recently. So the defining paper is probably the Wilkinson's 2016 publication. But when I read that, I was very happy that the crystallography open database from the very beginning followed most of these principles. Even so, these principles come as very natural set of rules to our field. So, for example, from the very beginning, the crystallography open database assigned a unique identifier and a stable identifier to each structure. And these identifiers are perpetuated through all the history of the database. I would like to note here that it's not necessary to use such identifiers as DOI for data sets, although that is possible as well. The most important thing is that these identifiers are kept stable and are unique, allow you to identify what data record you are talking about. On the left, I cite the table from the Wilkinson's paper that gives us an overview of what a FAIR data set is, or what a FAIR database is. And let's go through all these items and see how well the COD scores on them. It is important that data are accompanied by complete and rich metadata. And here we are very lucky to have the CIF framework, crystallographic interchange framework, established by the International Union of Crystallography and the community, the crystallographic community. And this framework already has in itself means to provide metadata such as bibliographic information, chemical information, or quality information about the data record. And I should mention that some of this information is added when the data is ingested into the crystallography open database and deposited there. So we actually collect data from several sources and metadata and make a consistent uniform record in our database. The database code as required is included into the record itself. And there is a web resource, an openly accessible database where you can look up all these records. Either you can use a search facilities of the crystallography.net server, or you can actually download the data and use your custom search engine on that. From the very beginning, we use standardized open protocols, and there are several protocols that allow you to access data. We offer our collection of records as rsync protocol through the rsync program. Actually, PDB also uses the same mode. Then all our data are in a subversion repository so that we can track the history of all changes in their database. and we offer access through the protocol of this version control system as well, the SVN protocol, and of course the web standard HTTP or HTTPS protocol. And this protocol also enables authentication and authorization when this is necessary, and this is necessary when you want to deposit your data. You can download our data without authentication, but if you want to deposit data, you need to present yourself. Now, at the beginning, it seemed that once the data are deposited into the Crystallography Open Database, there's no need for that data to disappear. But it turned out that occasionally, on rare occasions, we need to retract data. And we had such occasions. And here, our policy is that the data record stays there, but just the actual data atomic coordinates are removed. This is necessary for several reasons, and the most important reason is for everybody to know that this record existed. It was found. It was found necessary that this record is retracted, and we should not redeposit it again under different identifier. Again, metadata stay available as required by the FAIR protocol, even when the data themselves are no longer available because they're no longer considered to be valid. Interoperability of data that we present are guaranteed by the crystallographic interchange framework and adherence to its syntax. And also the semantics of that data is described in the CIF crystallographic interchange framework dictionaries that give machine readable definition of what each data item means and what their relations are, so that you don't need to guess this, and you have definitive source of that information. Also, the syntax, by the way, is currently defined in machine readable form as a Beckers-Naur form of CIF syntax, and so writing a CIF parser and validating a CIF parser can be done with mathematical accuracy. And we also work currently on establishing cross-references between crystallography open database and various other chemical databases, for example, PubChem, so that you, from knowing a crystal structure, you can easily find out what chemical properties and other properties, physical properties of that substance or compound was, of that crystal was. All this gives you a possibility to reuse the data, so you can ingest it into your programs or into other databases and conduct computations. The last item added actually to the crystallography open database was the license, and the data is, I'm very happy that the advisory board of the crystallography open database approved that. Data are available under CC0 license, so essentially it's public domain. We have full provenance from the very beginning of the crystallography open database, so we in the version control system. So basically we can answer the question who, when, and why changed any line or any bit in the file that you are getting from us. And of course, we use the quality criteria, the numeric quality criteria for crystal structures that are established by the International Union of Crystallography and are laid out as requirements for data publications in IUCR journals. Now, what is a good structure and what is a bad structure? What is a suitable structure? It depends to a great degree on the purpose for which we want to use data. So, for example, requirements are presented to data if you want to identify a material, or if you want to demonstrate that the compound is indeed the one that you think it is, and quite different and probably stricter requirements on signal to noise ratio and refinement quality are there if we want to do charge density investigations. Since data come into the crystallography open database from different sources and from different authors, this means that we need to record what people thought the quality criteria are, and these all parameters are included into the crystallography open data files. And this means that we are ready, we must be ready for unexpected reuse of the data. And this is the crux of the open databases, that you can reuse data, not only for the original purposes, not only for reproducing the research that people have carried out with it, but also for different things. And you can collect statistics on that data and use, for example, for machine learning or similar applications. So I think we are well positioned to do this as well. And from the ICR, we take the CIF framework. So as I've mentioned, we take the CIF syntax, we take CIF dictionaries and use those and adhere to those. In addition to that, we use dictionary definition languages developed by the ICR to add, to create additional data items that are in specific COD CIF dictionaries. So all data items, data names that we use are documented in a formal way. And also we do some checks that ICR mandates for publication requirements. They are similar but not identical to Platon alerts, which most of you know when you solve structures. So, and this essentially gives us a three-tier data validation procedure. Now, it turns out that not only we need to check data that comes into the crystallography open database, we quite often need to curate the data, so to fix some problems that are identified during the deposition process or afterwards. So we have established data creation principles, and the most important are the 7 principles listed here. So first of all, we try to stick as strictly as possible to the ICR standards and to the written standards. And this is important because if that were not the case, then, you know, one requirement would very soon come into contradiction with another requirement. So if we have a standard that says the file should be written, data should be presented in a certain way, then all software is expected to read such data. And if the software cannot do that, then the software needs to be fixed. But if our data doesn't conform to the standard, then we have to fix the data on our side. This is a clear responsibility assignment by using the ICR standards. Now, I think another very important principle is, and sometimes we need to resist that, we need not to invent data. It's very often we look at the file and see, oh, look, it has a mistake. We need to correct. We know what should be there. And we need to double ask ourselves, oh, do we really know? Why we think that we know that the atom should be in this position or that position, or the data, the atom name should be this and that. And the principle is, we don't invent data. We'll go into the original publications, occasionally contact the authors, and make sure that our records represent exactly what the authors intended to represent, to publish. And in case of doubt, we think that it's better to have no data than to have wrong data. All changes are recorded and explained in the crystallography open database records themselves and in the log messages. And originally we had just a free style text describing the changes and signed by the person who did them. But recently we have switched to structured changes. So you have different data items of that's a framework that say when the change was done, what is the aspect of the change, what was changed, and who changed it. Okay, so this now becomes machine readable. You can interrogate the changes and also take this into account when you do calculations. And of course, you can get back every revision, every version of the file that ever existed in the crystallography open database. And you can also find out where the data came into the crystallography open database. So there is a provenance of the original files that are being submitted into the COD. So as I said, we have three levels of validation, from the most formal and the simplest one, which is syntactic check, then to the still formal, but less formal, and more tricky validation check. And validation, and when I say validation here, I mean validation against CIF dictionaries. And then come what I call a domain-specific checks, such as internal consistency, coherence with raw data, how well the model corresponds to the observations, and how plausible the structure is. And all these are important, but these are already difficult to define formally and need insight, scientific insight, and sometimes expert opinion to figure out whether data are valid and correct. So the formalization goes down from the top to the bottom in this list, but also the value of checks increases, even though you lose the formal ability to perform them. So let's now have a look how these three checks are being performed. Actually, for each layer, we have a specific tool, which you can also use on your files and on your data if you would like. The CIF parse tool checks the syntax and tells you where the problem is. It also has possibility to correct some syntactic problems, which turned out to be important, as you will see later in this talk. And then there is a CIF validate tool that validates against dictionaries. And then we have CIF check for domain-specific checks, including the ICR numeric checks. These all tools are available in the COD tools package that we are distributing in Debian and Ubuntu systems. Okay, so let's look at how these checks perform on the crystallography open database files and on the files that are published in scientific press as supplementary materials. First, I want to note, and I'm quite happy about this, that all our files, to our best knowledge, conform to CIF syntax. So if you get a file from us, you can read it with the correct CIF parser. And if you can't, we will fix that. But what happens if you read files from the publications? Well, it turns out that even in the very recent years, as you see in the slide, that come occasionally files with syntactic errors. So from the 12,000 files that we harvested from the most prolific publishers, there were 14 files that were just syntactically incorrect. CIF parse, as you see, it catches this problem. And the reason why in this example the problem rises is that the quotes are missing. By the way, our CIF error correcting parser can fix many of these errors. And you might say, well, there is just 14 files, very few. Does that matter? Why should we think about this? What this situation tells me is that so the question is why this file appeared in the publication at all. If the reviewer would have looked into this file or would have tried to read it into any CIF processing program, then she or he should have noticed the problem and alerted the authors, and that problem should have been fixed. And this means that probably, I don't know, but I have a feeling that nobody really looked into that file during the peer review process. And syntactic errors are rare. They were more common in previous years, last century, but still they are not encountered often. So you would expect that maybe twice as many files as we have encountered here have syntax errors, and half of them were corrected. And this means that half of the files are actually not really peer reviewed properly. And this is, I think, a reason to worry, because those files that are formally correct can still have problems, and they are even more difficult to spot, as I told, than this formal validation check. So I would suggest, I would think we should all strive to give special attention to data peer review during the publication process, and when they go into the journals and supplementary materials. Another problem that arises is that sometimes the file might be syntactically correct, and so the parser doesn't find anything, but as was pointed by our users in the personal communication quite recently, the very data inside is not probably what the authors intended to say. Because if you look at this text, then the publication contact author contains strings that should be most probably were intended to be data items on their own. But now they are masked into a semicolon separated text field. Now again, you might say this is not a very important item, probably. The cover letter was probably processed on its own right, but we do encounter larger examples where part of the important data are masked by incorrectly placed text fields in some files, and this goes unnoticed. So unfortunately, our tools don't catch similar situations. So again, data review process should be established, and proper authoring tools that generate CIFs could help a lot, I think, in this situation. How much time do I still have? I think.
Say a couple of minutes. How much do you need to finish?
Well, can I have 10 minutes, something like
yes, that? Please.
I'll have to run.
Please continue.
Okay. So let's now look into the next level of validation against dictionaries. Here we have also IUCR helps us a lot. We have CIF dictionaries that formally describe each data name used in the structure files, and we can programmatically process different aspects, for example, value ranges and value types. We have recently created a CIF validate and tool, and also the CIF2 framework validation tool that uses new DDLM dictionaries, recently developed by the International Union of Crystallography. Now, when we ran this over all our records, then we were a little bit scared because we got 11 million validation messages from just 500,000 of data records. The situation is not that bad as it might seem on the first place, because in many cases these validation messages do not preclude us from correctly interpreting the data. They are more of syntactic issue, but sometimes they point to serious problems in data. For example, in the record which is cited here, the validator says that atom name is not found in the corresponding data tables, the corresponding loops. And if we look at the data, we see that extra character, for some reason, is appended to the atom name. For humans, this is not a problem to figure out that probably this name should be F40. But if you do automatic processing, then this atom will not be correctly identified. For example, you might not get correct temperature factors for this particular atom. This means that validation can catch important errors, and unfortunately, these errors at the moment in our database are masked by a large amount of spurious messages. And it would therefore be very helpful, and we suggest this in our recent publication, that these processes, this validation process tools, are used also during peer review and publication process. Okay, another example of the problems that we encounter during validations are data that look strange and seem to be corrupt. And I must notion that all these examples which I show you, they were not caused by our deposition procedure. We do check this every time. These come from the validation, from the publications themselves. Okay, so since I'm now really over time, so I'll have to quickly go through the slides that I have prepared. Another important validation procedure, which already goes into the third layer, for example, for is the internal consistency and the chemical plausibility validation. To this end, we have interpreted chemical structures for actually all collection of the crystallography database data, and these data are available and allow us also to check whether the published coordinates are consistent with other chemical identifiers, for example, with chemical names or with chemical files. Okay, and this already allowed us to spot on some problems and alert publishers who said that they will correct the issues and improve the data. Okay, so I will go over to conclusions now. So conclusions or recommendations. So as a researcher and educator, I would say it's very important that we tell our students and our colleagues that data and also formal aspects of that data are very important, can't neglect that because that will hamper interoperability. And for publishers, we could recommend that they use as many tools and give as many tools to authors as possible, also for data quality checks. And I trust that Julian, after me, will tell us a lot more about how internal consistency of the data can be checked. Okay, I thank my colleagues and the COD advisory board, and I'm ready now to answer your questions. And I see there is one question from Kamil.
Thank you very much, Saulius, for this excellent lecture. Yeah, we have even two questions. Several questions now. So Kamil is asking the following questions. Do you store the structure factors along with the atomic coordinates data resulting from the refinement results? The structure factors are available freely, for example, in the ICR journals.
Yes, excellent question. We do store structure factors when we get them, when they are published. So I had even the slide, which I skipped, which says we have, I think, 58,000 observed structure factor files matched to the structures. And also many structures have internally the Shellix structure, HKL data, which we should probably extract and put into the same format as the other structure factor data. And yes, you can get them openly.
Yeah, the second question from Kamil is, do you validate atomic coordinates against the structure factors?
Not yet. Well, partially. We check that the unit cell is the same in both structure factor and structure files. And strangely, we sometimes find discrepancies. But we don't do any deeper validation. This is planned. And both atomic coordinates and the corresponding structure factors are submitted. It is actually already possible now. We do it since several years by now, and everybody is welcome to submit both structure factors and the coordinates. We are now thinking about raw images, actually, that these should also be stored.
Oh, yes. The third, his question is following the other two. Do you think that it will be possible in the future, concerning the both atomic coordinates and corresponding structure factors are submitted? So as I understand, you have this in your plans.
Yeah, I read this. Indeed, this is possible even now, and this is being done by.
And Paulina, maybe next questions.
No, we don't.
Next question is from Harry Powell. Hi, Saulius. Thanks for great talk. I was wondering, you may have addressed this in your lecture when you were talking about FAIR principles. How do you flag entries in code that are subsequently shown to be fraudulent?
Such structures are marked with a special COD data name, which is called, I don't remember the name actually, need to look up, but it says that the structure is retracted. The same flag is present in the data tables, so that when you search for data, the retracted structures are by default not shown. The metadata and also cell constants and the chemical formula that was previously declared is still in the file, but the coordinates are replaced by dots, which means they are irrelevant. And there is a corresponding curation report that says this structure doesn't correspond to any real compound. Caveat emptor. Did I answer the question?
I think so. The next person, Marcin Koziel, Hi, thank you for great lecture. Do you think the CIF5 format is good or bad, taking into account all its applications in data processing and archivization?
Okay, that's a philosophical question, and I think for long-term archiving, CIF is a really good standard and a really good format. First, it's based on text, and I always tell my students we received most of our knowledge through thousands of years through human history in the form of text. So text is durable. Binary formats are much less so. And it has formal syntax and semantic specifications, and ICR are working to improve this and to build ontologies on top of CIF. So it's being developed. Now, of course, it has some features which probably, if you ask me, I would have done them differently. For example, the lack of termination signs sometimes leads to a situation where you just lose part of the file and there's no formal way to verify that, unlike, for example, in XML or JSON files. But, well, these were the compromises done back in 1990s, and they are not showstoppers in my opinion.
Yeah, we have next question from Simon Grabowski. Quantum crystallographic refinements, the wave function and/or multiple populations are as important for the reproduction of results as the structure factors. Do you see ways how to store and link such information along with the refined structures and structure factors? This is a big challenge that we currently face in the quantum crystallography community concerning data storage and availability.
Okay, so that's indeed a very important issue. So first of all, a dictionary and a vocabulary should be created. And I must admit, I don't know how far quantum crystallography community is on that way, but this is definitely doable. And for what I know, wave functions are large data files like raw images. So using text-based format for that is probably prohibitive at current stage with our current computers. But IUCR has been working on mapping CIF dictionaries into HDF5, a binary format, which is used for high energy physics. And that format allows to store large arrays of binary data, again, in formally described and specified way. So I would look into that, and I think wave functions could be stored and archived like in the form of HDF5 or similar files.
Before Piero finishes his question, he has already finished.
Yeah,
the multiple model is already included in the CIF dictionary since mid 2000s. Okay.
Yeah, that's true. That's true.
You already mentioned once raw data. Can you be a little bit more specific on this? Do you see any chance to somehow extend your data bank by creating like a super data bank which would contain also raw data?
That's true. We are thinking about how to store original data. So for regular crystallography, raw data images, which we do for our group, but we would like to also make a worldwide archive. And wave functions would go into the same category. Now, the challenge is, of course, a disk space, which is expensive. And we are thinking about a shared file system that would allow multiple institutions and interested communities join together forces, and so they back up each other's data, so that even when one institution has failure or withdraws from the system, important data are not lost. And one technical possibility, which my student is working now on, is a Tahoe LAFS file system. LAFS means least authority file system. So if I may, to take 1 minute, it's a very cool idea. You take a large file, for example, an image or a wave function file. You chop it into 10 pieces, and you use so-called erasure encoding, so that any three pieces of that file are enough to reconstruct the original data. And then you distribute this 10 pieces on different servers, so in different institutions, which means that you can lose 7 servers, 7 bricks, as they say, without actually losing the data. And this seems to be the way to go. Also, what it has, since this scheme has a property that those people who need data, they actually provide the storage. And so essentially the people who need the resource pay for that resource. We don't need somebody to pay for our data. So I'm thinking in this direction, and maybe we'll roll out something.
Well, people somehow pay for data, but how about paying for people involved? And do you have any, like, I don't know, grant project which would cover costs of development of your data bank?
Well, we do apply for Lithuanian Research Foundation funding, and we had some successes, but of course, success rate is not 100%, as you know. And we were lucky to have some European funding. Recently, we had a SALSA project that used our database, and it was very helpful to develop it. Well, we are looking for other possibilities, of course. And as I've mentioned also on the previous talk, this is not a stable income, but since we use very frugal methodologies, we use open source software, we use very flexible configuration of our computers, we can maintain data and keep data even with the minimum support from our university. And we did it for more than 16 years now. So I think this works.
So how big is your group which is involved in developing of this data?
We are now 4 people.
4 people. Yes, we do not see more.
I have a question, Krzysztof. So I wonder how you deal with a situation that from one set of structure factors you have several different models of atomic coordinates deposited.
That is handled quite easily because the structure factors are in separate files, and they are linked through the special data atoms, which we have defined in the COE dictionary with the structures. So basically, you can have multiple models that all point to the same FOPS file. And even more complicated situation arises in powder diffraction structures, where you can have several diffractograms and multiple phases can be refined against all these diffractograms. There, a powder diffraction dictionary exists that establishes how links between these files are included into the files, and we just follow this convention.
But it must be done by the user during the deposition, or?
The powder diffraction community, I didn't do it myself, these refinements, not yet. But I understand that the GSAS software and other software like that takes care about these links. So you upload the file. It can be a single file with multiple data blocks or several files, and our software just checks these links using the established standards. So as a user, you will get a message that, some link is missing. So you are missing this phase, or you are missing the diffractogram for this phase. But if everything is okay, then you just deposit the data. Now, I can't now remember the station where we had one single crystal data set and multiple refinements based on that. But technically, this can.
We are doing it very often, so or we.
I would be interested in talking to you more in detail about this.
Yeah, the problem is that usually there is no official way to record this information in the file. We can comment it only.
Well, if it's multiple models refined from one observed scattering factor file, then in the COD it's easy. You upload the first structure, assign the scattering factor file, the FOPS file, to it, and then you upload the next structure and say it has the same FOPS file as you uploaded previously, and you just say it's. And you can upload them with just a single archive, I think. But we need to see how this works. We didn't encounter such situations a lot. So if you send us your data, we would be very interested to look into it.
Okay, so another situation is that I'm taking data from your database and re-refine it and upload another model for the same data you already have in your database. So I guess this is the same problem, more or less, just different people are depositing the files.
Yeah, we planned for such scenarios, and you basically take your new solution, your structure gets a new identifier that's independent from the previous one, and we can occasionally say that this new model relates to the previous model, and yeah, maybe it has lower R factors or better fit data, and both structure files should specify the same FOSS file. And I think at this point, at this level, this solves the problem.
And how you deal with the situation that I know that there are SIFT dictionaries. They define very strictly what each field means, what it should contain. But from the practice, I also know that many programs are filling this. Sometimes are, for example, for fitting statistics, they are computing them slightly different way and are putting this information into exactly the same place in the SIF file. How to deal with this? I don't know. It's probably not possible to check by you if the statistics was computed exactly the same way as SIF dictionary is asking.
Well, if I correctly understand, the problem you mention is that people use the same data name.
Yes.
But use different algorithms to compute the factor. Well, this is indeed a problem, and the only way to get around this is to have one open source program that takes that data and computes all these criteria in the same way. It needs to be written carefully. We don't have such tool at the moment, but this could help. Other than that, well, how large are the differences in the computed?
They might be really important differences in terms of statistics. Maybe that it's not very important, but this somehow connects to the next question. In case of a standard kind of model of scattering factors, you can recompute it by yourself. But with quantum crystallography, you have so many different models. Even with multiple model, you can. The SIF is very well. We have very good SIF dictionary, but still there are some tiny details which cause that different softwares may give you a slightly different values. So it actually points to the question: should we also somehow store I don't know, software routines or something, because otherwise it's sometimes impossible to reproduce the whole procedure.
Okay, so this is indeed a problem. I can comment. I have several comments on this. First of all, in the development of the CIF2, the IUCR also introduced the DREL language. You probably know that. And DREL allows you to actually include small snippets of code into the dictionary that precisely specify in an algorithmic way how a parameter needs to be computed. So it says to get I don't know, the statistical criterion, this and that, you take that data, you add these, multiply this. It's an algorithm, and it can be actually interpreted by a suitable interpreter. There is sample implementation of DREL. I know it's not particularly fast and does not seem to be very widely used, but such possibility exists, and this would be one of the ways to go. Another way to go is, of course, to have software, preferably open source software, where you have a source and can compile it, and then make a good release cycle. So you write that software, assign it a version, say it's 1.2 version of that. And then in the CIF, you have data names that say that this particular parameter or this particular file was generated by this version of the software. Software audit metadata are in there. In that situation, you don't have the algorithm inside the CIF file, but you have the precise version of the software, the link, hopefully the link to the source code. You get the source code, you compile it, and you run it, and in theory, you should get the same thing. Now, many questions arise. Are your libraries the same? Is your operating system the same? Is your CPU the same? Take different CPU, you can get different results. All these things can be specified as well. And can they be reproduced? Well, we can fancy that you have a description of your CPU in a formal language, Verilog.
So this points once again that we should store the raw data, and maybe
yes,
at some point it should be just simply reprocessed, right?
And I very strongly would urge that we also use and have open source software in a well-defined language, programming language, which says how that software should behave formally. Then we have better chances to make our computations reproducible.
Yeah, thank you very much, Saulius. I do not question nor comments, so thank you for your great lecture and discussion.